Okay, hopefully you can all hear me. Um, so good to have everything muted. I've been having technical difficulties, so hopefully this goes well. If it doesn't, I'll figure out something else. We're gonna play it by ear. I'm gonna make I'm gonna make a couple short recordings instead of one long one. I think that'll work better in the long run. First thing we're going to talk about is limits. The previous sections should be review, so hopefully you're good there. If not, I've posted some resources, and you've got the book to look through. You can always contact me if you're stuck on some pieces. So, all right, I had written all of this out, but it's in another file, and I can't open it here, so we're going to make it work. Limits. So our limit is we're looking at, my professors always described it as, what do your neighbors think? We don't care about what you think. What do your neighbors think? Oh, that is Mobius. He is expressing his opinion on limits. Hi, go away. I'm busy. Okay, so let's get a happy little graph here. Sorry, hopefully he'll go away in a minute. If not, I don't know. Hi, they don't care about your opinion. Yeah, you're loud. All right. So how we express, oh, sorry, you just jumped up. Limit as x approaches 2. So our function here is x plus 1. Can you hear him purr? He's purring right now. So we look at our x value, x plus 1. Or no, x approaches 2. This is x equals 2. So we mark this point, and we're looking from either direction. What is our function? What is our graph doing in this case? So from the right side, as we go down towards 2, we get, and wow, my brain is foggy today. We get x goes to, it looks like 3. Let me rewrite this. Limit as x approaches 2, and my function is x plus 1. You can put it in parentheses or not. So from the right side, it looks like it's moving towards 3. And if we look at it from the left side as well, we're also moving towards 3. So we can say our limit is 3. So yeah, you're just looking at what your function is doing near the point. So we can have a case where we have a hole there, but the limit will still exist. So we'll talk about that more probably in another video at this point. So let's say, whoops, we have a hole right here. We can still look at limit as x approaches 1. Our hole is at 1, and this is just plain x. So at 1, our function doesn't exist, but our neighbors say, hey, we're moving towards 1, and we're moving towards 1. So our limit is just 1 here. All right, let me move down my other page. I deleted that. Okay, so that's our basics of limits. This is a very simple example. We'll get to more complex ones, but it's basically saying what's x doing, or like what's our function doing at this point. And I will save this document when I'm done. Hopefully it'll look good. If not, we'll survive. All right, so let's talk about our more formal definition of a limit. Apologies for my handwriting. I swear it will get better as the semester goes. Let me just write this down and then explain it. can leave now. Bye. Okay, so our formal definition of a limit is if our function f of x becomes arbitrarily close to a single value or single number L as x approaches c from either side, then our limit is L. So our c is, it's a weird way to write it, is our x value, and our L is our y value. I used to get those two mixed up. So C is what X is doing, L is where our Y ends up in this case. Okay, so some very basic limits. We're going to let B and C be a real number. So that's epsilon. So it's basically they're inside the real numbers. So recall your real numbers are your positive and negative whole numbers, your fractions, your decimals, your numbers like pi, root 2, e, anything like that. It's basically not imaginary, which is root negative 1. And then your n is a positive integer. So z is integer. The little plus in the corner means a positive 1. I will use these symbols a lot, so get used to them. They're common math symbols. Um, worst comes, you can find like a guide to them online somewhere. All right, so limit as x approaches c of some b value is b. So these are all going to be limit as x approaches some value c. So basically, this is a constant function. There's my xy axis. I'll get my blue out here. If my function is constant, it's always b. So in this case, if my x equals 2, which is apparently my favorite number today, that's y equals 2. Oof. I should drink more coffee. Okay. So no matter where we choose on this graph, y is always 2. So that's our basic function. 2 limit as x approaches c of x equals c. So we'll get more into this as we go, but you plug in your value if you have a nice polynomial like this. So if your x is always y, like they're the same, it's our regular line, our standard line. Then they're always the same. Third one, the last two are, in my opinion, the same rule, but they separate them. If you have x to a power, the limit is just c to that power. Very straightforward. And their last one is related, like I said. Okay. If we have an nth root of x, you're just going to plug in c, you'll get the nth root of c. The only thing to be careful, if n is even, c must be positive or non-negative. Because then we get a square root of negative, we turn into imaginary numbers, and we live in the real number system. So be cautious of that. Okay, the more properties, or the rest of the properties we have, looks like we have 6 of these guys. And then I'll make a different video for more things. Wrong thing. A lot of these work really nicely and work just like you want them to. Not all of them, but many of them. So if we have a polynomial, we just plug and chug. We can plug in our limit, our value for our limit, and call it a day. B is still a constant. Our f of x is a function. I forgot to write in. Let me write this in blue. Limit as x approaches c of f of x equals some value L. Limit x approaches c of g of x equals k. And our b and c are constants, as they were in the above. So we'll need that. So basically this says if you take a constant times our function, our limit is the constant times the limit. And we'll do some examples. The examples aren't very interesting until we get these properties. Okay. If we're adding or subtracting two limits, we get the addition or subtraction of the limit itself. So if we are two functions, limits, whatever. So f of x plus or minus g of x, our limit is going to be L plus or minus k. Again, it works like you want it to. I keep forgetting you can't see my other screen, so I just want to refer to that. I swear this will get smoother, or maybe it won't. Okay, if we're multiplying two limits, hey, or two functions, we multiply their limits. Again, works like you want it to. Then if we divide, mostly works like we want it to. This is where things get a little dicey. We'll deal with a lot of these. As long as your k isn't 0 at this point, or isn't 0, we can do this. We can divide our limits. The problem is sometimes it is 0. Limit as x approaches c, f of x to the n is L to the n. And this is our related one. Limit as x approaches c, nth root of x, oh, whoops, f of x, not x, equals nth root of L. And just recall the nth root of something is that something to the 1 over n power. In your calculators, you probably have this guy. You might not have. Calculators are a great tool. I highly recommend using them when you can. Some of these you're not going to be able to use, but when you can, do that. I know when I was learning how to do some of these math things, if I couldn't figure it out on paper and pencil, I'd throw it in my calculator and kind of reverse engineer what we were doing. It helped me make sense of it. So I highly recommend. I didn't write down any examples for these. What is wrong with me? All right, I will make some up. All right, we're going to use baby numbers. I think most of the numbers in your problems aren't going to be too bad. So we've always had positive limits so far. So x goes to a positive number. This time we're going to throw it into the negative one. So we're going to use all of these rules. Well, the first couple. So your big thing to watch out for limits is, are you going to have a negative under the radical, or are you going to have a 0 denominator? In this case, we can't have either because it's a polynomial. So we're good. In that case, we're just going to plug in. So my limit as x approaches -1 I'm going to say -1 squared plus 3 times -1 minus 2, which equals 1 minus 3 minus 2. 1 minus 5 is -4, I really hope. So our limit is -4. We're using 2's and 3's today and 1's. So limit as x approaches 3. I have x squared minus 1 on top and x plus 2 on the denominator. And if I look at my denominator and if I were to plug in 3, I get 5. So we're safe to use the rules above. We don't get a 0. So I can just plug in, and this gives me 3 squared minus 1 over 3 plus 2. 3 squared is 9 over 5, which gives me 8/5. Sadly, fractions are going to be a fact of life. I will do many things avoiding fractions where I can, but we can't always avoid them. We just kind of have to live with it. All right, do I have any other good examples? All right, I think, no, we'll do this last part. Sorry, I was trying to decide what else I wanted to do. All right, the second video, the follow-up video, will probably come later today. It's going to take me a bit to get this online. All right, so our methods for finding limits, we've used 2 of these before. This is super technical. You graph and you eyeball it. So basically you graph your function and say, okay, what are we doing? What is the left and right limit? Do they agree? What are they going to? That's our limit. The drawback to this is graphing takes a long time if you're graphing by hand. If you're going into Desmos, which I should put a link for, and graphing that way, it's not as bad. You can usually get an exact answer, but it doesn't always let you have an exact answer. What happens if your answer is pi? If you graph it by hand, you may not see that. So it's nice to get a picture, an idea of what your graph's doing. This will tell you if your graph doesn't exist at a point or if your left and right limits don't agree, but it's not as practical as some of the others. Method 2 is what we were just doing. Or no, it wasn't what we were doing. Similar. Plug in neighbors. Okay. So we're going to have another baby limit just so this is easier. Limit as x approaches 1, x plus 1. What we're going to do is plug in numbers near our value. Oops, that should be. So I'm not going to plug this in. This is great if you have a something on the denominator that makes this gross. We can plug in stuff close. So if I were to plug in 0.99, I get, or 1.9, I can't read today, 1.9, 1.99, 2.01, 2.1. And you may want to plug in numbers that hit here or here, but it really looks like our limit is getting close to 2. So we're going to say this equals 2. This will not give you an exact answer, but it'll sometimes tell you if you're in the right ballpark. I would go through and struggle finding a limit at a particular point because my function was nasty. This would give me an idea of what I should be looking for. So I like nice little checks. I think homework is going to make you do that, but avoid it if you can. The last method, two of them really, are plug-in methods. Factoring is going to be big in this class. If you're a little shaky on factoring, I know I posted some good resources for you to look at, so look at those. There are sheets online where it tells you common ways to factor, so look for some of those. My first one, I'm going to do exactly that, is factor using one of these. All right. We have limit x approaches 2 of x cubed minus 8 all over x minus 2. Now, if you notice, if we plug in 2, we get 0 over 0, which we can't do that. We can't get over 0. So, get rid of that. I have to manipulate. You should always write your limit as x approaches 2, da, 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 as you go, just so you know it's a limit and you're allowed to do what you're doing. It's picky. On top, we have what's called a difference of cubes. These always factor into diamond space. A minus B. Let's scoot you over. Sorry, it's been a minute since I used this. Here we go. I don't use this pen very often anymore. All right, so you get A minus B, A squared plus AB plus B squared. If you have time, go find the sum of cubes. It factors very similarly with two differences. This is a good fact to know how to do these. So go find them. And if you're not sure how I got there, go backwards. So FOIL and see what you get, or expand, I guess, in this case. So my numerator turns into x minus 2, x squared plus 2x plus 4 all over x minus 2. I don't really need to put that in parentheses, but I'm going to. Now, I have an x minus 2 on top and on bottom. I can factor those out. Rewrite. X squared plus 2x plus 4. Now I don't have any denominators anymore. Yay. So I can just plug in 2 squared plus 2 times 2 plus 4. 4 plus 4 plus 4 is 12. A little different than what it looked like when we tried above, like when we had a 0 over 0. It's not the case. So watch for those, factor, reduce, simplify, do what you can, and see what happens. This is the sort that if you're unsure what you should be getting, you can use either graph it or the method 2 up here, plug in its neighbors, and see what it's going towards. That's not the final answer. It just gives you an idea of where you should be. Okay, the last sort I think are the trickiest of them all, but once you know the trick, it's really not terrible. We're going to find the conjugate. We're going to conjugate our problems. So example is the best way to look at this. I actually don't know what this final solution should be. I should have figured that out. So if you have a radical or sometimes your trig, I don't think we do trig in this class, but sometimes your trig functions would be nice. If you have something plus or minus something else and it's just, you can't figure out a way to deal with that, what you do is you take the problem piece. So in this case, the top. Put that in parentheses. I leave the first thing as is. And I take my second thing and I change its sign. And then we have to make sure to do the same on top and bottom. Otherwise, we've changed our function. Can always multiply by 1. Now, I FOIL. Get the right pen. No. Please. My first terms will give me root x plus 1 squared, which is just x plus 1. My first, I don't remember how to FOIL order. Plus 1 minus 1 minus 1 minus the insides, root x plus 1, then the outsides plus root x plus 1, all over x times x plus 1 plus 1. All right, you'll notice this should always work out that the radical is going to cancel because we have positive root x plus 1 and negative root x plus 1. They go away. And in this case, our 1's cancel as well. Excuse me. So we do this when we have the conjugate. It's like saying a minus b times a plus b, which is a very nice thing. It will always give us a squared minus b squared. So this is a helpful trick. We are left with limit as x approaches 0. I have an x on top. X times root x plus 1 plus 1. Now I can cancel off my x's. This leaves me with a 1 on top. But plug in 0, I get 1 over root 1 plus 1, which is just 1/2. So very useful technique. Your factoring will always come back again and again. So we used a positive this time. If you have, say, color pen in my hand. If you have like a root x plus 2, your conjugate in this case would be root x minus 2, etc. Okay. I am going to stop this here. Where's my recording button? All right, oh, there it is. All right, I'm gonna stop this here. I'll make another video later, but this should get you through most of the limit section. There's 2 pieces left, I think. One-sided limits and unbounded limits. Those aren't terrible. Those are gonna be another video though. This is long enough. So if you're having trouble hearing this, let me know. If you have any other technical issues with this, please tell me. It's hard for me to know if nobody lets me know. So, all right, thanks.